Greetings everyone and welcome to my presentation. First of all, let me thank you all for coming here today. I'm Omar Tariq and we are Team 3. The theme of our project is to employ epistemic planning for robotic theory of mind and implicit collaboration. During the next 10 minutes, we'll be discussing about the introduction, the replication and improvement progress, the current problems and their proposed solution, and the modifications from the original plan. The idea we got to implement epistemic planning for human-robot collaboration is from this baseline paper by Lasse Dissing and Thomas Bolander. Let me briefly introduce the theory of mind. The theory of mind is reasoning about other agents or robots and their worldviews. Having a theory of mind means having the ability to understand and reason about the mental state of other agents or beliefs. False belief tasks such as Sally-Anni task domain shown in the slide used for testing the strength of a theory of mind. The task contains the two human participants, Sally and Annie, standing behind a table with three objects, which can be put into three different containers. There can be multiple objects in a container and the content is not visible without lifting the lid. The human participants, Sally and Annie, can interact with the environment by moving objects in and out of the container and by entering and leaving the room. The robot keeps track of all the interactions with the environment. In this experiment, Sally puts an object in the first container and leaves. After Sally leaves, Annie takes the same object from the first container and puts into the second container. By doing so, the robot ends up with the false belief. The robot is then asked a series of questions revealing whether the robot has correctly modeled the beliefs of the participants. One of the potential advantages of simulation theory of mind is that it may help robots become more communicative with humans, and such robots would run an onboard program that models their own behavior in combination with what other objects and people. The architecture outlined here represents a computational model of artificial theory of mind. First, the model clearly provides a robot with the ability to self-model and hence predict the consequences of its own actions. Secondly, the model can also be used to predict the other dynamic agent's actions and if they interact, the consequences of the robot's actions to that other agent. Now, it comes to mind that why are we using the symbolic AI to solve this problem instead of deep learning complex methods? Symbolic AI is usually understandable and has more explainability. In symbolic AI, the computer first needs to understand the universe of the problem, specifying its objects and rules until the computer can make its own assumptions on the basis of these rules. Now let's discuss our current progress. There are some of the changes that we did to implement our project in a more simplistic way to conserve the project timeline. To pass the false belief task, the original paper has implemented open pose tracking, face recognition, and Apple track detection algorithms in real time to keep track of the actions of human agents, cubes, and boxes. In our simulation environment, we propose to implement the same action tracking mechanism using April tags to simplify the overall scenario. This is a simulation of the environment in which the dynamic robot with onboard camera is keeping the track of April tags, and we can get the information of the tags IDs, their position, and their orientation in XY coordinates. You can also see on the left terminal. This is the first step to keep the track of actions done by the agents on the cubes and boxes with April tags attached on them. This simulation environment is being modified further according to the scenario presented by the base paper to test the false belief tasks. Our current challenges involves to keep track of the actions between two agents and their interactions with the cube and boxes, and so we are working to solve this issue.
From now on, I would like to elaborate on motion planning. Before the planning, it's required to build a world model that describes the environment. In the original paper, there was a single robot and the two humans named Sally and Annie manipulating an object by picking and placing into the container. Please note that the paper authors used three objects and three containers in the environment. In contrast, in our world model, there's 3 robots. We replaced the humans with the mobile manipulators, which is the combination of your 5 manipulator and the head of mobile robot. Robotic was used for the gripper, and another difference from the original paper is that we substituted 3 containers with 2 baskets. The others tested their model directly using physical robots. However, we would like to validate the model in simulation, since this simulation is cheap and the easiest implementation. We have chosen physics-based simulation called Gazebo, and we have implemented motion planning by using MOVEit framework with OMPL Planner. OMPL means Open Motion Planning Library, which is a powerful collection of state-of-the-art sampling-based motion planning algorithms. OMPL is also default planner in MOVEit. Currently, we can plan and execute the UR5 manipulator from a start position to a goal destination. The short demonstration is illustrated in the slides. We are doing a simple pick-and-place implementation. However, the pick-and-place using UR5 robotic gripper on MOVEit 2 planning scene is not still working. We are trying to solve the minor issues with gripper control, multi-robot control, also cannot load the full environment from simulation to RVs. The main challenge is that there are issues documented about MOVEit that uses C++ and Python. So in MOVEit, grasping is done using the MOVEit group interface, and that interface actually defines various poses and departures involving in a grasping operation, but there are no report that works in the migrated in Python file.
Now we're coming to the main component of the paper, the dynamic epistemic logic engine. This engine should have 2 major components. One, it should be modeling the dynamic knowledge of the different agents and such of the walls that they are believing. And second, it should be implemented as an engine. It should be easy to integrate into any new project, and it should be easy to interface to the project. The authors didn't publish any repository or any available code. However, in a more recent paper, they published like an optimization of the epistemic engine, improving the runtime. However, this epistemic engine is highly coupled to the experiment, and the interface of the implemented engine is really hard to make a usage in any other project. Also, we look into any public repositories and we couldn't find any dynamic epistemic logic. We could find epistemic logic model checkers, but these have like a top-down approach, while the dynamic epistemic logic engine has like a bottom-up approach. Therefore, we implemented our paper from scratch using modal logic and cryptostructure. The cryptostructure also models the beliefs and the connection of the walls between the belief states of the agents, and also they have some loops, so we can model the n-order belief system between different agents. Second, we wanted to implement it as an engine and have a clear interface so we can use the engine as a black box. We achieve this by implementing it as a REST API. The REST API contains 3 major endpoints: rested sees an event, rested resets the wall into a ground state. The sees use define the vision between the agents, and we can model if 2 agents are in the same room with the vision. And then there is the event. That means like an agent has done an action into the wall and has modified something into the wall. Here we have the call into the inputs of the engine. So first of all, we define like Sally and Annie sees each other. They have vision between 2 of them, so they are in the same room. And second of all, Sally moves a cube into the box 1. And in the right, we have the defined cryptostructure for these 2 calls. Second of all, following the Sally-Annie experiment, we say like Sally and Annie don't see each other. So Annie don't see Sally and Sally don't see Annie anymore. That means that they're in different rooms. And second of all, Sally moves the cube into the box 2. And in order to move into the box 2, also it has to be not in the box 1, as in here in the call. That creates this cryptostructure. And then here we can find out that Sally knows that the cube is in the box 2. And also Sally knows that Annie knows that the cube is in the box 1. And also here we represent like Annie has a false belief, since the information that she's getting is different from the real world mark with a dot in the center of the world. This is the information that we're getting as a response from the epistemic engine. In this response, we have the n belief system, n beliefs of each of the agents. So here we can say like Annie believes that the cube is in the box 1, but also knows that Annie believes that Sally believes that the cube is in the box 1, since Annie didn't saw Sally move in the box. Now we can compare what is the real world, that is the cube in the box 2, and also we can compare like Annie believes that the cube is in box 1. Since this one is not representing the real world, we know that this is a false belief that Annie has. Some of the challenges that we have found using the epistemic logic engine is that the dynamic epistemic logic never forgets. So all the worlds that are being generated in the model, we cannot delete them. And second, we have the issue that every time we have a new event, that is a dot product with the world. So we are generating a double amount of worlds every time we have a new event, and that has an exponential growth of worlds. So now what is coming to next, we have shown that we can pass the Saliani test with the robot, since we have integrated the computer vision, the dynamic epistemic engine, and the virtual environment, simulating the test of the paper. So right now we want to integrate the belief system of each of the agents with automated planning. So we want to integrate the beliefs into the precondition of the actions of the PDL, so we can implement an implicit collaboration framework for robots. Thank you for listening.